Welcome to this video. So in this video we are going to discuss electric vehicle routing problem. So this project is done by 4 members. Their names are Sachin Kumar Yadav, Saurav Kumar, Prantik Manji, and Vaibhav Vishal. So let's start with the introduction. So as we can see that there is rapid growth in the carbon footprint, and also the temperature is rising due to global warming, due to the carbon and other oxides. So many countries in the world, all over the world, are shifting their focus from the fossil fuel to the more greener energy alternatives such as solar energy and hydrogen energy and all other stuffs. So in this trend, EVs are becoming a game changer and providing a better alternative for the classical petrol or diesel automobiles, which helps in the transportation and logistic purposes. So their production and application has grown rapidly over the years. We can see that EVs performs better in many aspects such as energy efficiency, low transportation cost, and lesser pollutant emissions. But it still suffer from some disadvantages instead of those advantages before. We have to, like, they are powered by the batteries only, so we have to recharge them time by time. And we also the recharging also takes time, and the energy of the battery also depends on the weathers and conditions and all other things. So these are the problems. So we have to kind of like find the root for the problem, which is a non-deterministic polynomial hard problem, NP hard problem. So it is kind of we can reduce this EVRP problem to the TSP problem. So that's why the EVRP problem is an NP hard problem, and it is difficult to solve or to obtain an optimal solution in the polynomial time. So the problem consists of two sub problems, which are the routing optimization problem and charging decision problem. Like, for routing optimization problem, we have to select the optimal route in the given graph, or like routes. And the charging decision problem is whether we decide to charge or not. The routing optimization for EVs are dependent on the limited battery capacity, and we need to charge on the basis of the available charge. And we have to distribute the load among the customer nodes. And the charging decision is basically based on the whether we can reach our destination with remaining charge, or we need to recharge our vehicle or not. We There are also two different approaches other than the classical brute force approach or CSP based approach. Those are heuristic based approach and meta heuristic approaches that used to reduce the time complexity of the problem. But these approaches may lead to suboptimal solution or suboptimal allocation of routing problem, but they give the solution in polynomial time, or like reasonable amount of time. So coming to problem statement, so in this slide we are going to discuss both problem statement and the assumption we have assumed while solving the problem. So in EVRP, we assume we have considered a kind of network, city, like network of city as our system. We have different nodes. Basically, we have different nodes with three categories. One are the customer nodes, Second will be the depot, at which every EV has to start from the depot and should return after delivering the goods to the depot. And the third type will be the uh, charging nodes, at which we can recharge our electrical vehicle if needed. Apart from this, we need to basically pick up some amount from a customer node and drop some amount to that customer node. Those are denoted. Also, we have k homogeneous electrical vehicles at the depot, which are used to pick up and delivery to the to the customer nodes. We also assume that every electrical vehicle can carry at most a capital W amount of weight, more than which it cannot carry. The vehicles start from, as mentioned earlier, vehicles start from depot and in its journey to the depot. Initially, it has the full battery when it leaves the depot. We also assume that the consumption of energy is dependent only on the weight of the vehicle and the distances it cover while delivering and picking up the stuffs. It also depend upon some constant alpha, which will be calculated by different parameters such as climate and the condition of roads, traffic, etc. We also assume that a vehicle cannot run if it has the capacity below 15%. That's all. And also, when it reaches to charging station, it will charge with a constant rate, like linear constant rate. And also the charging will be done on first come first serve basis. So the main objective of this problem will be, we have to select an optimal path for the electrical vehicle in order in order to optimize or minimize the energy consumption, overall energy consumption. And also we have to satisfy all the customers, that is, we have to pick up and deliver the required amount at each customer node. So now we are going to discuss three distinct algorithm or methods that we have proposed in this work, which are A star based algorithm, like kind of modified A star based algorithm, CSP based algorithm, and meta heuristic based algorithm. So these algorithms, so as we know, CSP based algorithm are NP hard, so we can obviously find the optimal solution, but it will not give us optimal solution in polynomial time. Also, A star and meta heuristic may give a reasonable solution, but but not near optimal solution, but not optimal solution may not be in a reasonable amount of time.
Hello everyone. Now I will discuss about CSP based algorithm approach. So first of all, I will discuss what is CSP. CSP is a mainly known as constant satisfaction problem, where we define some variables and some specific domains and also some constants, such a way that each variable will assign some domains and also have to satisfy some constants. Okay, this is the main approach of the CSV. So, in I have told that CSV has variables, domains, and constants, and also CSV is widely used like scheduling, resource allocation, puzzles like Sudoku solving is used. Okay, mainly we have to assign each variable some domains and have to satisfy some constants. That is the main approach. Okay. So I'll discuss the core concept that is used in our EVRP problem. So first of all, I am defining some variables. What will be the variables? first of all is route variables. Route variables means that the node which is visited by the vehicle V at step S. Okay. Then the resource variable. Resource variable means that each vehicle would have some load, okay, and each step, and also at each step or at each node, every vehicle will have some different kind of energy, like what is the remaining energy is present. Okay, so we have defined what is the variable type. Variable type is root variables, and what is the domain? Domain is depot, charges, and customer nodes will be this domain. So load variables, what will be this? Load variables will range is 0 to what is the maximum vehicle capacity. And energy variables. Energy variable is 0 to what is the maximum battery capacity. Okay. Going to the next slide. Okay. And what is the constant in our EVRP problem? The main constant is that structural constant. Like we have to start from a depot and we have to come in the same location, that is the depot, and also we have to visit each customer and satisfy their needs. Okay, and also I have some resource constants, like every time I'll have energy in each vehicle is more than at the certain limit. If it is falls down the certain limits, we have to go to the charging station and have to charge. And also have to constant the weight. Like each vehicle have certain kind of weight capacity. So we have to always check that what is the current weight of our current load on our vehicle. So what is the physical limits? Physical limits that vehicle, each vehicle can load maximum its capacity. More than that, its capacity cannot load. So what is the energy consumption? And next is energy consumption. Energy consumption, we have defined some formulas, like alpha is a hyperparameter and the distance between two nodes, and what is the load in the current vehicle. Okay, I'm going to the next slide. Okay, so I'll discuss some pseudocodes for the CSV based algorithms. So okay, by the pseudocode, first of all, I will load the data. What is the data is present in the. First of all, I will load default charges, customers data, vehicle count, capacity, energy parameters, and distance matrix. I'll load it. Then I will initialize our CSV model. To initialize this, I will create some variables. The variables is routes. Routes means that each vehicle and each step means each node. What will be the node? Load means each vehicle at each step. What will be the load? Or means the cargo weight. In such a way that each vehicle at each step will have some remaining energy that we have to maintain. Going to the next slide. So we also in the CSP pseudocode have some constant, like we have start from the same route, same start node, and go back and come into the same endpoint. And each customer should visit it exactly once. And also we have initial load. Initial load means each vehicle would have initial load, initial load capacity, and we have to each node, like each customer have certain kind of uh, like certain kind of things to do, like have to do pick up or have to do delivery. Okay, and every time we have to see that we cannot exceed our capacity. And also energy constant, initial energy will be full capacity of the battery. And also what is the current consumption? Current consumption is alpha into distance into current load. And if the any kind of thing that our energy is low, then we have to charge. And also have to satisfy that in energy variable constant, we have to satisfy that energy cannot be negative. Okay, energy will not be negative. And also the valid transition in the distance matrix. Okay, and the valid transition over distance matrix. That is my pseudocode. Thank you.
Hello everyone, I am Saurabh Kumar. I am going to explain the method A star heuristic waste algorithm for minimizing the energy consumption during finding the routing plan. First, we will see the overview of A star algorithm. In A star algorithm, we know we need the value of Fn, which is calculated as a summation of Gn plus Hn, where Gn denote the cost to reach the node n from the start, and Hn denote the heuristic estimate to reach the goal from n. We will see the how this algorithm is working. Here we take a two list, open list and closed list. In the open list, first we add the initial node and we calculate the Fn value for the initial node. Here you can see we take the initial node as a S0. Then we will take a loop where first we enqueue the node which has minimum Fn value. Uh, if that node is a goal node, then we'll return part. If that node is not a goal node, we will see the others node by calculating again the G and H value of that next node until we will reach to the conclusion. Now come to the next slide. Uh, Here we take the state as a tuple where V is denoted as a current location of uh, vehicle, L is the current vehicle load, E is the remaining battery energy, V is the set of visited customer nodes, G is the energy cost accumulated so far, and H is the estimated to goal. Here we will see the state transition and the how we will take the heuristic so that our uh, energy consumption is minimum and that will give a good routing plan. Here we will see how this transition will work. Here from initially if we are at node V and we move to the next node V dash, uh, their energy changes is given by the alpha into the distance between the that node and the load carried by the vehicle. The new energy, yeah, remaining energy of that vehicle is E minus delta E. If V dash is the customer, their load will be calculated as following. We have to pick up and we have to also deliver. Here we are using that minus TV plus PV and we will update the visited node as shown in this image. If V dash is a charge or default, then we will not do any changes in load. But if we will have to recharge the vehicle to maximum E energy. Here we can see in more details how this transition are working. You can also see for the Charlie node. Now come to heuristic. Here we take a heuristic Hn is equal to alpha into shortest distance from V to depot into load plus set of visited customer into penalty. Uh, this is a two parts. One part is this and other part is the U into penalty. Now here this heuristic is admissible. We can see uh, in our A star uh, heuristic this return to depot energy estimate the energy required for the vehicle to return to the depot from its current location and the unvisited customer penalty. This is the two step. In the here we can see if in reality actual energy is will likely be higher due to the longer route and heavier future loss. Thus, this term underestimates the true cost. If we take the second part of the heuristic, this term does not reflect real energy cost. It simply encourages exploring path covering more unvisited customer. It does not overestimate cost. It may even underestimate. Therefore, the full heuristic satisfies the this equation where H star n is the true minimal cost for n to the goal. So we can say this heuristic is admissible. Now we will see how outputs look like. Here, generally for the our input, there are three vehicle and some some of the customer nodes and charge node. Here we can see for the electric routing plan for the vehicle one, energy used per segment is calculated using the formula alpha into D into L. We can see for the vehicle 2 also and vehicle 3. So here we can see in the graph from the depot vehicle 3 start and go to the customer node 0 and then it again come back after pickup and delivery. Similarly for the vehicle 1 which is denoting in red, it will first go to the 1, then it will go to the 13, then it will come to depot. Similarly, vehicle 2 first go to the node 9, then go to the node 10 and come to the depot. Now, now key takeaways here we can see A star efficiently plans energy-aware vehicle routes with realistic constraint. Heuristic include depot return estimate and customer visit incentive, state transition capture, deliver, pickup and charge dynamics, admissibility guarantee optimality of the computed plan. Thank you.
Hello, dear friends. Today we are going to see a meta-heuristic algorithm. We have implemented our electric vehicle routing problem with meta-heuristic algorithm also. First of all, we are going to see meta-heuristic algorithm. It is a high-level strategic design to find a near optimal solution for complex optimization problems. It do not guarantee global optimality, but are effective for large NP-hard problems. It involves intelligent search mechanism like exploration and exploitation, balance between randomness, diversity, and guidance intensification. Its examples of metaheuristic are genetic algorithms and colony optimizations, particle sword optimizations, simulated annealing, etc. Key characteristics of heuristic algorithms are it can skip local optima. Unlike basic heuristics, usually stochastic involve randomness, flexible and problem independent. Now let us see EVRP, electric vehicle routing problem, is an NP-hard problem, computationally intensive and difficult to solve optimally for large instance. Exact methods are impartial for large problem instance. Heuristic and meta-heuristic methods are needed for feasible solution. Key steps in genetic algorithms we have used: initialize population with valid vehicle routes, evaluates fitness of each solution, total energy consumption, select elite solutions, top 5% for reproduction, perform crossover and mutation to generate new individuals, replace the old population with new offspring and repeat the process. Solution encoding, where we have done like this: each individually present a set of vehicle routes, chromosome. In meta-heuristic, there is a chromosome offspring and things are used like a biological terms are used. Genes represent customer visit, charging station and depot locations. Example: depot where our vehicle is initially, and now it served customer 1, again it served customer 2, and let us say it's charging dropped less than 15%, or it is not able to reach the depot again due to less charging. Then it goes to charging station and then it has reached the depot. Now let us these are the input formats we have taken.
distance matrix between depot customers and charging stations, customer demand, depot capacity, and energy parameter. Energy model is, we are using energy model like E is equal to alpha into load into distance, where alpha is some hyperparameter, load is weight that vehicle is carrying, and distance is the distance between the two nodes. Algorithm settings we are doing is like population size, we have used 100 to 500 individuals, mutation rate is 0.01 to 0.1, light count is 2 to 5% of the population. Core loop of genetic algorithm is, for each generation we are evaluating the fitness for each individual solution, then select the top, we are selecting the top individuals, then applying the crossover and mutation generate offspring. These are two methods used for generate offspring, preserve the elite solutions and replace the old population. These are the pseudocodes how we have solved our problem. We have first initialized the population with we have seen in the previous slides how we have what we have done. This we have done initialized our uh, initialized our what we can say initialize our populations, and then we have done the maximum generations we have done. Now we have solution, we have generalized now generated initial cell population. In meta heuristic we have to first generate one population, and then we are going to mutate or mutate, then we are going to mutate on the next solutions and check whether the our new solution is good or not. This we have done like this. Now we are checking for parent 1 and parent 2, and then we are generating the child segment, you can see there. Then remaining nodes we are calculating and returning the child. There is a mutation function we have written, which are doing happening like this. And this is the fitness function we have used in our meta heuristic approach. That's it. In fitness function we are calculating their penalty 10 to the power 6 into unserved customers are the penalty if they have, they if the if our algorithm left any nodes any if our algorithm not visited any nodes, or 10 to the power 3 into extra vehicles is also a penalty if if any vehicles not scheduled. Okay, thank you.